Modern military bases are built for conventional threats. They are designed to withstand missiles, aircraft, and large-scale assaults. But a new threat is emerging, small, cheap, and everywhere. Drone. Warfare is changing how bases can be attacked. The goal is no longer destruction, but disruption. Throughout the Cold War and the decades that followed, military base design was shaped by the threat of large-scale airstrikes and missile attacks. Defense planners assumed that any serious assault would come from high-speed jets, precision-guided munitions, or ballistic missiles. To counter this, bases were built around a doctrine of layered protection. Surface-to-air missile belts formed the outer shield, with radar-guided systems like the Soviet S-75 or the American Nike Ajax, positioned to intercept incoming aircraft at altitude. Early warning radars scanned the horizon, feeding data to central command posts buried in reinforced concrete bunkers. Inside the perimeter, hardened aircraft shelters protected valuable fighter jets from blast and shrapnel. These shelters, often made of thick, reinforced concrete, were spaced to prevent a single strike from destroying multiple assets. Munitions depots and fuel storage tanks were separated by hundreds of meters, limiting the risk of a chain reaction in the event of an explosion. Runways were designed with rapid repair in mind, with engineering teams trained to lay down prefabricated panels and restore flight operations within hours of a strike. Communications nodes and command centers were placed deep within the base or in underground facilities, reflecting the expectation that only heavy bombardment could threaten their function. This approach reflected a fundamental belief: survivability depended on physical hardening, redundancy, and the ability to absorb punishment from a powerful, conventional adversary. The entire architecture was built to withstand a handful of massive attacks, not a steady drip of small, precise disruptions. Base layouts, security protocols, and defensive investments all flowed from this logic. The assumption was clear: if a base could survive the initial onslaught, it could continue to operate, repair damage, and get back in the fight. Mass production and miniaturization have fundamentally altered the calculus of attacking military bases. Off-the-shelf electronics, once reserved for hobbyists, are now the backbone of weaponized drones assembled for less than $1,000. Brushless motors, lithium polymer batteries, and compact FPV video links allow these systems to be built quickly and in large numbers. In Ukraine, open-source data and battlefield reports confirm that commercial quadcopters modified with simple explosive payloads have become routine instruments of disruption. The adoption curve has been steep. In 2022, drone attacks on infrastructure were sporadic. By 2025, Ukrainian and Russian forces were launching dozens, even hundreds of low-cost drones in coordinated waves. The frequency of strikes on airfields, fuel depots, and radar sites has increased by an order of magnitude compared to the early years of the conflict. This rapid escalation is not limited to state actors. Non-state groups in Syria and the Gulf have leveraged the same commercial supply chains, bypassing export controls and military procurement cycles altogether. The essential enablers, miniaturized electronics, open-source flight controllers, and 3D printed airframes, have made scalable disruption possible. The Ukrainian battlefield, in particular, has served as a laboratory for these tactics. FPV drones, piloted in real time via analog video links, can navigate around jamming and strike with meter-level precision. The result is a persistent, low-cost threat that does not aim to destroy a base outright, but to degrade its ability to function. Attackers now have the means to impose operational costs and uncertainty on even the most hardened installations, forcing defenders to rethink the logic of static protection. Runways form the backbone of any airbase. Even a single crater from a small explosive drone can halt flight operations, as aircraft require an unbroken surface for safe takeoff and landing. During the 2023 attacks in Ukraine, a 200-gram FPV drone left a runway unusable for nearly 2 days. Engineers had to patch the damage before sorties could resume. The operational impact ripples outward. With the runway down, no reinforcements or supplies can arrive by air, and combat aircraft are stranded on the ground. Fuel storage is another critical node. Fires triggered by drone strikes can burn for hours, forcing crews to shut down pumps and isolate damaged tanks. In Luhansk, a single drone ignited a diesel tank, cutting off fuel for frontline units for 2 days. Without fuel, generators fall silent, vehicles stop moving, and flight operations stall. Ammunition depots present a different risk. Even a minor explosion can set off a chain reaction, scattering shrapnel and forcing the evacuation of entire sectors. Ukrainian after-action reports show that a cluster of drone strikes on a mortar stockpile created a 72-hour delay while unexploded ordnance was cleared. Every hour lost means fewer rounds available at the front. Communications nodes, often housed in small shelters or antenna masts, are especially fragile. Damaged fiber optic links or shattered radomes can take 36 to 72 hours to repair. During outages, commanders revert to backup radios, slowing decision cycles and reducing the flow of real-time intelligence. Radar sites and air defense units are the base's eyes and shield. A drone strike that disables a primary radar array can open a blind spot for hours, shortening warning times for incoming threats. In one documented case, a 2-hour radar blackout allowed enemy artillery to strike forward positions with little warning. Each node, while small in footprint, holds outsized importance for the base's ability to operate under pressure. Attackers now rely on a playbook that values sequence and repetition over spectacle. Instead of single, overwhelming strikes, they launch small drones in staggered waves, each time to maximize disruption rather than destruction. A first wave might crater a runway or ignite a fuel tank. As engineers mobilize to repair the damage, a second wave arrives, targeting the same or adjacent nodes before repairs are complete. The result is a cycle where defenders are forced to split their attention and resources, never fully regaining control of the base's critical functions. Battlefield reporting from Ukraine and wargaming analyses from NATO and RAND highlight how these staggered attacks are calibrated to exploit repair and response windows. For example, drone salvos are often timed just as runway patching teams finish their work, forcing them to start over and extending operational downtime from hours to days. When multiple nodes, like runways, fuel, and communications, are hit in overlapping cycles, the base's ability to coordinate defense and sustain operations erodes rapidly. This cumulative burden is not accidental. Open-source doctrine documents and after-action reports describe attacker decision cycles that prioritize exhaustion. By launching drones in intervals, sometimes as short as 15 seconds apart, sometimes spaced by hours, attackers force defenders into a reactive posture. Ammunition depots, communication shelters, and radar arrays are struck in succession, overwhelming available repair crews and creating persistent gaps in the base's defensive envelope. Over time, even small, low-cost drones can impose strategic paralysis, not by destroying everything at once, but by denying the base the breathing room needed to recover. Detection remains the single greatest technical challenge for defending against low-cost drone attacks on military bases. Unlike conventional aircraft or missiles, Small drones have a radar cross-section as low as 0.01 to 0.03 square meters, comparable to a large bird. This makes them difficult to distinguish from background clutter, especially at low altitudes where ground reflections can overwhelm X-band surveillance radars. Many drones now operate with radio frequency autonomy, flying pre-programmed routes, or switching off their control links after launch. Without an active radio frequency signal, traditional spectrum monitoring tools lose one of their main cues for early warning. Even when detection is possible, the economics of interception are starkly unfavorable for the defender. A single intercept missile can cost upwards of $1 million, while the drone it targets may be assembled for less than $1,000. In the Ukraine conflict, defenders have sometimes been forced to use Patriot missiles that cost $3 million to shoot down drones, costing $500. This creates a cost-exchange ratio that is unsustainable over time, especially when attackers can launch dozens or hundreds of drones in coordinated waves. Attempts to close the gap with electronic warfare or directed energy systems have shown mixed results. Radio frequency jammers can be effective, but autonomy and frequency hopping reduce their impact. High-energy lasers, while promising in tests, still struggle against fast-moving drones with a low radar cross-section at operational ranges. The current model, one expensive interceptor for each cheap drone, cannot scale. As a counter-UAS technologist recently noted, we are trying to solve a $1,000 problem with a $1 million answer. The result is a persistent vulnerability. Defenders face a technical and financial dilemma, unable to guarantee protection against a threat designed to slip through both sensors and budgets. Protecting every inch of a modern base from waves of cheap drones is no longer realistic. The old model, fortifying runways, fuel depots, and command shelters, meets a new reality. Attackers can disrupt operations at a fraction of the defender's cost. Planners now face a stark choice. With every critical node exposed and limited resources, which assets deserve the most protection? The answer is shifting. Instead of chasing perfect defense, military doctrine is moving toward resilience. The focus turns to mission continuity, accepting that some damage will happen, but ensuring the base can keep functioning. Investments now go to rapid repair teams, redundant power and communication lines, and dispersing supplies across multiple locations. Fuel might be stored in several underground bladders instead of one tank. Communications are duplicated, with mobile backups ready if primary links fail. Every layer of counter-drone defense, including radar, jammers, and interceptors, must be budgeted with the knowledge that some drones will get through. This approach forces tough decisions. More redundancy means higher costs, but greater survival. Success is measured not by stopping every attack, but by how quickly operations recover. The doctrine of invulnerability gives way to the art of staying in the fight. Today, the gap between base design and drone reality widens. Fixed infrastructure offers predictable targets for cheap, adaptable threats, eroding operational continuity with each strike. As disruption becomes the metric of success, the challenge is clear: adapt defenses now, or risk critical systems rendered silent at the moment they are needed most.